We now would like to study the properties of what we call an ideal transformer. Now, here what we have is we have some type of voltage source. That's our input. We write that as VP is our input voltage. It's oscillating in time. That's what we call our primary. And what we have here is, in this picture, an iron core. And what that does is it channels the magnetic field lines around the iron. Remember, magnetic fields cannot begin or end on any point. And so in our ideal transformer, all the magnetic field lines are confined to travel around this iron rectangular solid shape. And notice on the other side, we've wrapped a number of turns on what we call the secondary side. On the primary side, there's less turns in this particular picture. So our primary has NP turns. And what we're doing is we're going to generate a voltage across the secondary by Faraday's law. The secondary is what we call our secondary, and that has NS turns. Now, because it's the same magnetic field through inside on both the primary and the secondary side, that's our ideal transformer, there's no loss of flux, that what we have is that the flux through each turn is on the primary side is equal to the flux through each turn on the secondary side. Remember, flux is just the magnetic field times the cross-sectional area. Now, from Faraday's law, that we know that we're going to generate a EMF on the primary side with N turns in the following way. That the flux on the primary side and the voltage are related by the number of turns on the primary times the rate of change of the flux through one turn on the primary side. And on the secondary side, that's the number of turns times the rate of change through the flux on the secondary side are the EMFs that are generated on the primary and the secondary side. These are our EMFs. Now, this is through one turn. So when we equate our ideal transformer has, through each turn, there's no loss of magnetic field. So the change in flux through the primary and the secondary are equal. And that means that this is VP over NP, and this is VS over NS. And so we have that the ratio of the voltage across the secondary divided by the primary, that's VS over VP, is equal to the number of turns over the secondary divided by the number of turns of the primary. So in this case, we see, in our example, you can see visually that there's more turns on the secondary. When N secondary is greater than N primary, that implies that the voltage across the secondary is greater than the voltage across the primary, and that's what we call a step-up transformer. Now you'll see a beautiful demonstration of a step-up transformer in our demo videos. And when NS is less than N primary, that tells us that the secondary voltage is less than the primary voltage, and that's what we call a step-down transformer. And we have a lot of applications in real electrical networks where voltage is stepped up, transmitted at a high voltage, and then stepped down in a number of ways so that it's at a lower voltage when it gets into your household, which will be some nice conceptual questions that you'll answer. When we talked about our ideal transformer as a step-up or step-down transformer, in this case, because in our visual picture we had that there were more turns in the secondary than the primary. This represented a step-up transformer. Now let's look at what happens to the current for an ideal transformer in which there's no power loss. Now recall that the power in the primary, so this is power, is given by the EMF, which we said was V primary, times the current in the primary. And in the secondary, so this is for the primary. And in our secondary, the power in the secondary is equal to the voltage in the secondary times the current that goes through the secondary. Now, for an ideal transformer, and then we'd have to close the circuit here because at the moment there's no current flowing through the secondary, so it would be when we close the switch. Now, in an ideal transformer, we have that there's no power loss, so the ideal transformer, of course, everything heats up, energy does get lost. We get Vp Ip equals Vs Is. And so we have the current in the secondary divided by the current in the primary. Current in the secondary divided by the current in the primary is equal to the voltage ratio V primary over V secondary. And when we analyzed our transformer here, we had V secondary divided by V primary, number of turns in the secondary divided by the number of turns in the primary. So this is actually the inverse relationship. This is the number of turns in the primary divided by the number of turns in the secondary. So when we look at this ratio, we see that when the number of turns in the secondary is greater than the number of turns in the primary, this number is less than 1, then the current in the secondary is less than the current in the primary. And when the number of turns in the primary is greater than the number of turns in the secondary, we're stepping up the current. And in our experiment,